Hello and welcome everyone to the video lecture of EC3030. So in this video lecture we will continue our discussion on memory. So in this video lecture we will be talking about DRAMs, Dynamic Random Access Memory. We'll basically see how a DRAM works. Alright, so in the previous lectures we have seen the memory hierarchy, and what we have seen is that there are registers L1 cache, L2 cache, L3 cache, and then we have the main memory, and then we have secondary storage and tertiary storage. Now among them, the main memory is made of the DRAM, Dynamic Random Access Memory, and also L3 cache might be made of a special version of DRAM which is called EDRAM or embedded DRAM. So we will mostly be talking about the DRAM, which is the building block for the main memory. Alright, so DRAM, you have seen DRAMs whenever you want to purchase a computer, a PC, laptop, or even the phones. So the terms, for example, DDR2, DDR3, all these things refer to the DRAM. So for example, this is how a DRAM chip looks like. So for example, if you are going to buy a MacBook, one of the specs is this 8 GB memory or 16 GB memory, or however much memory you want, and this memory actually refers to the DRAM. Alright, so now the first thing is that DRAM is a random access memory, meaning that irrespective of the physical location of the data inside this memory, the time you will need to retrieve a data, meaning that a read a data or write a data, will be independent of the physical location of the data inside the memory. So essentially what you have is a 2D array. So a RAM is always a 2D array, and for example you want to access the data that is here. So what you will get from the CPU is the address of the data. So this data, for example, in this case is an L bit data address, and among the first k bits, for example in this case, refers to the column number, and the rest of the bits of the address refers to the row number. So by the row decoder and the column decoder, you select this cell over here, and and then depending on whether you want to read or write, you push the data, write the data into the cell, or you read the data through this circuit over here. And you can access one bit of data or multiple bits of data using these peripheral circuits. All right. So the main storage element, the storage element in a DRAM is a capacitor. So capacitor is the simplest form of a storage element where the data is stored in the form of a charge. Alright, so for example here this is a capacitor, and the way capacitor makes is very simple. So you have a dielectric and oxide material sandwiched between two metals. So say for example this is an oxide, this is a metal, this is a metal, and this is a simple capacitor, and this capacitor can store a charge. For example, in this case, if the capacitance is Cs and it has a voltage Vs across it, then the charge in this capacitor, the charge stored in this capacitor is Cs Vs. Now you can define the data, whether there is a data or not. For example, if there is a data, you say that the data stored is 1, and in this case the voltage across the capacitor, say, is VDD, and that means the charge stored in it is Cs VDD. On the other hand, if you say that you want to define a data 0 stored in it, then you will say that the voltage across this capacitor is 0, and as a result there will be no charge no charge stored in this capacitor, meaning that the charge Q will be equal to 0. So this is how we define the data that is stored in a DRAM capacitor. Alright, so this is how a DRAM cell looks like. So again, you have this capacitor Cs over here, and then there is an access transistor. Now when we were talking about SRAMs, there also we talked about additional true transistors, which we call the pass transistor. Now here the access transistor plays the same role. So it essentially controls the access to the capacitor, meaning that through this access transistor, you can read or write the data that is stored in the DRAM capacitor. Now just like you have seen in the SRAMs, there is one word line for the DRAM and there is one bit line for the DRAM cell. Now remember, for an SRAM you had two bit lines, bit line and bit line bar, but for the DRAM you have just one bit line. Alright, so now this is how a DRAM array looks like. So each cell is connected to a word line. So word lines are these horizontal lines, and each cell is connected to one bit line as well, which are the vertical lines. So now here in each row I am showing only three cells, but these cells can go up to say number n. So in row 1 there are all these n number of cells, in the row 2 there are all this n number of cells, and similarly in the third row there are this number of cells. Right, and similarly in a column there can be n number of cells. So the last cell in column 1 will be n1, in column 2 it will be n2, the last cell, and in the last cell of column 3 the last cell in the column 3 will be n3, and as a result in this array there will be n multiplied with n equals n squared number of cells. Alright, and to select a specific cell we have to put a voltage VDD to that corresponding word line and also activate the corresponding bit line. So word line and bit line is used to select and read or write from or into a cell. Okay, so we'll look into this into more details. Alright, so let's first look at how we write into a DRAM cell. Okay, so the first thing to do to write into a DRAM cell is to put the desired bit into the bit line and then activate the word line, meaning that we put a voltage VDD into the word line to turn on the access transistor. Okay, so let's say we want to write 1. Okay, so write means that this capacitor, what you want to do, this capacitor, what you want to put a charge this capacitor up to a voltage of VDD. So what you will do is first you will put the bit line voltage to VDD, okay, and then you will put the word line to a voltage of VDD. Now putting a voltage of VDD will turn on this transistor, and as a result this capacitor, this node of this capacitor will be connected to the bit line, and irrespective of what the charge here in this capacitor is, this voltage will appear across this capacitor, and as a result this capacitor will be charged at a voltage of VDD. This capacitor will be charged at a voltage of VDD. That means that there will be Q amount of charge across this capacitor, and Q will be equal to CS VDD. Alright, now let's see what you say you want to write a 0 into this DRAM cell. So again what you will do is you will put the bit line voltage to 0 volts, and then you will put the word line voltage to VDD. So putting a word line voltage of VDD, will we turn on this access transistor. Now whatever the value of the charge that is stored in it, or whatever the value of the voltage across it, because there is a zero voltage, this capacitor will discharge, and as a result the amount of voltage across this capacitor will be zero, and as a result the charge across this capacitor will also be zero. And this is how you write a 0 into a DRAM cell. Alright, so let's see how you can read, you can write into a specific cell. Say for example you want to write a value into this cell 22. Okay, so alright, so what you need to do is first put this VBL2 to whatever value that you want to put in. Say for example you want to put in let's say you want to put certain voltage, so we'll say that V data, and V data is VDD if you want to write a 1, or V data is equals to 0 if you want to put a 0 into this 22 cell. Alright, so this VBL2 is set to this value, and VBL3 and VBL1 and all the other bit lines are basically floating, meaning that there is no voltage that has been applied here, and these are floating, meaning that there is it's not connected to any voltage source. It's also not connected to ground. Alright, and then you activate this word line, meaning that the voltage of this word line 2 becomes VDD. So this transistor turns on. Okay. On the other hand, all these word lines are at 0 voltage. So VWL is at 0, V word line 3 is 0, and all the other word lines are at 0 volts. Okay. So that means that this transistor is off, this transistor is off, meaning that all the access transistors are off except this, all the transistors in this column, access transistors, are off except this one. Alright. So now because this access transistor is on, so this capacitor over here will be charged to this V data voltage. So that's how you write this capacitor here. Now note that this access transistor is on, also this access transistor is off or on. However, this will not change the value that is stored in, for example, cell 23 or 21. The reason is that in these two cases, this bit line 1 and bit line 2 or 3 are floating. As a result, it won't charge or discharge the capacitor in 23 or 21. Only it will change the voltage or the charge of the capacitor in 22, because this bit line voltage is at a certain voltage, V data here. Alright, so now let's look at how a DRAM is read. Okay, so the way a DRAM is read is this. So the bit line is first charged at a voltage V pre means pre-charged. So the bit line is first pre-charged at a voltage, and usually this V pre is VDD by 2. Now remember, for an SRAM, you used to pre-charge both the bit line and bit line bar at VDD, but for an SRAM you pre-charge the bit line at VDD by 2 or something around VDD by 2. Alright, so next, the second step is to put a VDD in the word line so that the access transistor is turned on. Okay. Now then what will happen is that depending on the voltage across this DRAM capacitor, this bit line will change. The voltage at this bit line will change. So if the data that is stored here is 1, then this bit line voltage will increase toward VDD. So it will increase from, say, VDD by 2 to higher than VDD by 2. Okay. On the other hand, if the data stored here is 0, then the bit line voltage will reduce from VDD by 2, and then by monitoring the voltage of this bit line using a sense amplifier, you can find out what is the value, the data that is stored in this capacitor. So one thing to note here is that after you have read a 0 or a 1 in the DRAM capacitor, the voltage across the DRAM capacitor actually changed. Now means that every read operation actually destroys the data that is stored. So usually what is done is that, not usually, every time what is done is that after a read operation is done on a certain cell, whatever the value is read is again written into the DRAM cell. So we will look into how this is called the restore operation, and how the restore operation is done after reading a DRAM capacitor. Alright, so let's first look into the case when you read a 0, data 0 from a DRAM. Okay. So first what we have said is that we will pre-charge the bit line to a voltage, and let's say we select this bit line voltage to VDD by 2. So this is step 1. Okay. Now then we will put a voltage of VDD into the word line. So this will activate this access transistor. Now what we have said is that the data here is 0, meaning that the voltage across this capacitor is 0. On the other hand, this voltage is VDD by 2. So as a result, charge will flow into the DRAM capacitor through the access transistor, and as a result what will happen is this. So if I plot the voltage at the bit line, so VBL, then initially this voltage will be at VDD by 2, and then for example here we activated the word line, meaning that we applied a VDD voltage to the word line such that the access transistor is on now, and as a result what will happen is that the bit line voltage will start going down, and then what will happen is that the sense amplifier that monitors the voltage at the bit line will sense that the bit line voltage is going down, and it will say that okay, this specific cell was storing a data of 0. Alright, so now let's look at the other case where the data stored is 1. Okay, so that means that the voltage at across this DRAM capacitor is VDD. So again, the first step is to pre-charge the bit line at a voltage of say VDD by 2. So it doesn't have to be VDD by 2, it can be a little bit larger or smaller than VDD by 2 as well, but the first step is to pre-charge the bit line to VDD by something around VDD by 2, and the second step is to apply a VDD here, and this will turn on the access transistor. Okay. So now what will happen is that this capacitor is at a voltage of VDD. On the other hand, the bit line is pre-charged at VDD by 2. So what will happen is that charge will actually now this time flow from the DRAM capacitor into the bit line, and as a result what will happen is that the bit line voltage will go up. So if I plot how the bit line voltage changes as a function of time, so the x-axis is time, y-axis is bit line. So initially the voltage is at VDD by 2, and then we activate the word line, and then what will happen is that the voltage at the bit line will increase from VDD by 2. So now the sense amplifier that is connected to this bit line will see that the voltage is increasing, and then it will say that okay, the DRAM capacitor was holding a data that corresponds to 1. Alright, so now the important thing is that, as we have seen, as we read the DRAM capacitor, what happens is that the value that was stored in the DRAM capacitor gets destroyed, meaning that if there was a 0 that was stored in the DRAM, then the charge was flowing from the bit line into the capacitor, and as a result the voltage was then increasing from 0 to some value that is smaller than VDD by 2, but still it's not 0. On the other hand, say there was a data 1 that was stored in the DRAM capacitor, what we have seen is that as soon as we do a read operation, the charge was flowing from the DRAM into the bit line, DRAM capacitor to the bit line, and as a result the voltage across the DRAM capacitor was decreasing from its initial value of VDD to something less than VDD. Again, the main thing is that after reading, the original value has been destroyed and it has to be restored. And essentially the term that is used is that the read operation of a DRAM is destructive. Now compare with an SRAM. In an SRAM, once you read it, the data does not get destroyed. On the other hand, in a DRAM, the read is destructive. So it is a destructive read. So as a result, what you need to do is every time you read a DRAM cell, you have to write it as well. So what usually happens is that after you read the the decision that the sense amplifier makes, meaning that say a sense amplifier sees that the value that was stored in the DRAM capacitor was 1, then what it will do is after it has done the read operation, put a voltage of VDD into this bit line while the word line is still activated at VDD. In other words, so after it has done a read operation, it will keep the word line voltage to VDD and then put a value of VDD at the bit line if it read a data 1 and across the DRAM. On the other hand, so it will put a value of VDD if it read a 1. On the other hand, it will put a 0 voltage if it had read a data of 0 in it. So again, you first select a cell, read the bit, and after you have read the bit, you have to rewrite the bit that was read. And this is called restore operation. And the reason you have to restore the bit after you have read is because the read operation is destructive in a DRAM cell. Alright, so now let's look at the array level operation. So again, what you will do to read, say for example 2 is to first put a voltage of something around VDD by 2 in this bit line where BL1 and BL3 will be floating, and then you will activate this word line 2 by applying a voltage in this word line of VDD, and that will turn on this access transistor, and then depending on the data stored here, this bit line voltage will go down or go up, and once you have the sense amplifier has decided what it is reading, then it will put back the same voltage, the voltage corresponding to the data that was read into the bit line, so that the data is rewritten into this DRAM cell. Now note that again, when you are accessing this cell 2, the other word lines are at 0 volts. So as a result, nothing happens. So as a result, this transistor transistor is off. So nothing happens to the cell that was data that was stored here or the data that was stored here. However, these transistors are also on in the same row, but because BL1 and BL3 are floating, again nothing happens to this data stored over here. So the data does not change in cell 2-1 or 2-2 even though the access transistor is on, simply because the corresponding bit lines are floating, and also nothing happens to the cell 1-2 and 3-2 simply because the corresponding access transistors are off. Okay, so one of the important things about DRAM is the refresh. It essentially means that if you have a DRAM, you actually need to refresh the data values quite often. And the reason is very simple. Say, for example, you have a data 1 that is stored here. So basically, you have a voltage of VDD here. Now, this word line is not selected, meaning that this transistor is off. Okay. But still, what happens is that, as we have seen earlier, that in a transistor is never a ideal switch. As a result, there will always be an off state current that will be flowing through this transistor. And as a result, what will happen is that the charge that is stored in this capacitor will always get discharged through the bit line, meaning that if you plot the voltage Vs as a function of time, you will see that initially, although the voltage was VDD, it will slowly go down as a function of time. So what requires to be done is that this DRAM cell, each of the DRAM cell in the array needs to be rewritten at a regular interval. So for example, so this is T refresh, and after T refresh a read operation is done, and then the data is written back to it, so that the voltage here will become VDD, and then it will start grouping again. And similarly, you can think about similar situation where there is a 0 voltage stored in this DRAM capacitor, and in that case, due to the off current of the access transistor, the current will flow into the capacitor, and as a result, the voltage will increase with a function of as a function of time. And similarly, after every at a regular interval, you have to write the data back into the DRAM cell. So usually what happens is that that every row is refreshed at a of the order of 100 milliseconds. For example, 64 milliseconds for as an example. So if the refresh time is 64 milliseconds, that means that every DRAM capacitor will be refreshed, meaning that read and then restored every 64 milliseconds. And also, this requirement of the refreshing operation on the DRAMs gives it the name dynamic, meaning that the DRAM cells has to be refreshed dynamically, meaning that every at a regular interval it has to be refreshed, and that is the origin of this term dynamic. Now this is different from SRAMs. So in an SRAM you do not have to refresh the cell, and this is why the term static is used to describe the other type of memory that we have seen, that is called SRAM.